Hi, my name is Konstantin, and I have a problem, an infinite search problem. And because infinite search problems are really hard to actually search through, right? It might take a long time. That kind of made me sad. But thankfully, one day I had an epiphany that maybe instead of searching this infinite space, I could just search a finite space instead. And I kind of had an intuition that if I wouldn't find any elements in this finite space, that would give me a guarantee that I also wouldn't find anything in the large space. And this is really cool because now I can use well-known techniques like SMT solvers to solve my finite space and then learn something about this infinite space that I actually care about. So this made me happy. But now there's one additional thing that kind of bothered me. Now I had to rely on this reduction. And first, I wasn't quite sure that I was actually right that this reduction worked. And second, I also wasn't quite sure that I had implemented it right. So that's why I came up with the library that I'm going to talk about in this talk called SpaceSearch. SpaceSearch allows you to express these search spaces in the Coq proof assistant and then efficiently search them using an SMT solver. And this has the great advantage that now you can use Coq's powerful reasoning capabilities to actually prove your reductions right. So I saw that you guys like t-shirts. I didn't actually plan ahead, but I did find a white t-shirt and a Sharpie, so I hope this works. Okay, it didn't work so well with this. Sorry, guys. Okay, maybe I'm just going to be a bit more stationary. So okay. Oh, God. What is? Oh, no, it actually works. Yeah, probably a little bit. Okay, so next I'm going to, I gave you kind of a very high-level overview of what my problem was. But let me be more specific, thanks, about the actual problem that I was trying to solve. And to understand that, let me talk to you a bit about how the internet actually works, and in particular, the Border Gateway Protocol. So first of all, this is like a depiction of the internet, and what you see here is that it's not just one big network, but instead it's a network made up of smaller networks, here represented by clouds, and each of these clouds is administered and operated by an individual internet service provider, or ISP for short. Now, when these ISPs need to exchange packets with one another, they need to also exchange route announcements. And they do that using the Border Gateway Protocol, or BGP for short. And they do that by just propagating route informations to all of their neighbors, which propagate it to all of their neighbors, and so forth. And so far, this sounds like a pretty standard protocol, but what's kind of neat about BGP, and also what makes it hard, is that ISPs have a lot of freedom to configure their routers in any way they want. So for example, they might want to block some of these route announcements to a neighboring ISP. And they do that using very low-level distributed configuration, and that leads to tons of bugs. For example, just a week ago, Google accidentally leaked some of their BGP announcements to Japan and took out half their internet for several hours. And that's not good, right? Another time, the United States, or a Chinese ISP, accidentally attracted lots of US traffic, including military traffic, and the DoD wasn't so happy about that. Or YouTube went down because Pakistan had accidentally misconfigured some of their routers. So you see, it's a very, very brittle system, and when things go wrong, it usually has mass media attraction and governmental reports and so on, and you really don't want that. So to solve this, I came up with a tool called Backpipe. Backpipe takes in a configuration of the ISP, a specification of what the ISP actually wants, and then it either tells you that a specification is correct or that it's not correct. And so the high-level property that we want to check here in Backpipe is that for all possible traces, so all possible ways in which we can forward route announcements through our ISP, it must be true that the specification that we have holds. And it's easy to see here that this is an infinite search problem because the internet keeps running forever, so I can get route announcements on and on and on. And so this is actually quite hard to check naively. So thankfully, in one of my last papers, I was able to come up with this reduction that allows me to instead search a finite search space instead of this infinite search space. And this is quite nice. But again, as in the introduction slide, the problem is here that now I have this reduction that I need to trust. But at least I can verify it with coq. Right? I can verify this reduction if I express this in coq, which I can do with the SpaceSearch framework. And then SpaceSearch allows me to translate this to SMT. And I'm going to show you now how that actually works. To understand how the SpaceSearch framework works, we have to first rephrase this property that we want to prove a little bit. So what we're going to do here is, instead of saying for all possible traces my check needs to hold, we're going to rephrase this as, let's look at the set of all possible traces. Then let's figure out just this small subset of counterexamples, right? That's the subset of traces where this check does not hold. And then we're going to search this space. Now, if we don't find any element in the space, then we're golden, right? That means that for all possible traces, the check never fails. However, if we find a counterexample, we know that this is not actually correct. OK, and now I can tell you how we can construct these spaces using the SpaceSearch library. So first, we have some simple construction functions, like empty creates the empty SpaceSearch. Singleton creates a space with just one element in it. Union combines them. And this starts to look like a monad, so we need bind as well. So there you just apply a function to every element in a space and union all of the results. And this is kind of the interface that you get to construct spaces. And we also have an interface to eliminate them. So we have the search function. If you pass it an empty space, you're going to get none. If you pass it a space with elements in it, you're going to get one of the elements back. OK, with this in mind, we now know how we can implement this check in Backpipe. What we're going to do is we're going to first we're going to construct the space of all the initial traces. And again, this is a finite set. And so all we have to do is use these singleton and empty and bind operations and so on to construct this set. Now, the next thing that we're going to do is we're going to bind over this space. So think of this as just like picking one particular trace and looking at that, and then doing that for all of them. Now, for one particular trace, we're going to check whether the specification holds. If it holds, we return empty. If it doesn't, we return a single counterexample. Now, what does this mean? This means if the check actually works for all traces, then we're going to return empty for every trace. Bind is going to union all of these empties. We're going to get empty, and the search is actually going to return none. If, however, we have a counterexample, the search will find the counterexample. OK, so we're one step closer to getting this to be run by an SMT solver, but we're not quite there yet. So how can we actually efficiently execute this code that we have here? To understand that, let me first introduce you to the rosette programming language. The rosette programming language is an extension to the racket programming language that kind of extends the interpreter to also enable symbolic execution. So you can create symbolic variables and make assertions and then search for assignments to symbolic variables such that you avoid assertions, for example. So let me actually show you a little bit on an example how to do this. So in this example, we're going to verify De Morgan's law in rosette. So how we do this is that we create two symbolic Booleans, x and y, that corresponds to the for all quantifier. Then we're going to have an expression here that represents our formula up here. So right, it's and x, y should be equivalent to not x and not y, or that and negate it. And now that we have the expression, we're going to search for assignments to these symbolic variables such that the expression does not hold. So we're going to search for a counterexample. And this is like a pretty long-standing theorem in mathematics, so we don't expect there to be counterexamples. But essentially what we're going to do is we're going to assert false whenever they're equal. And this is a little tricky, right? We're asserting false in the case where things are going right. And if things aren't going right, we're going to return a counterexample. And solve is going to try to assign x and y such that we're not getting any assertions. So this is only going to work when there is actually a counterexample. Okay. Now that we have this rosette program, there is an algorithm called type-driven state merging that allows us to actually translate this to an SMT query. Okay. So now back to SpaceSearch, right? How this actually works is that we can now translate all our SpaceSearch kind of functions into functions in rosette. So for the union, what we're going to do is we're going to create a symbolic Boolean and kind of non-deterministically choose either the left or the right element in the union. Note that all of this is, we have all of this wrapped in funcs just to deal with differences in Rackett's evaluation than in Cox evaluation, but don't worry about that too much. The empty set is just an assertion of false, and searching we do using solving. Okay, so how are we going to stitch this together now? So what we're going to do now is we have this program written in Coq, and now what we're going to do is we're going to extract that to rosette or Lisp, and we will replace all these functions that we have here, like bind and search, with their rosette equivalents. And now we can efficiently execute this code. And basically what we have is a verified version of Backpipe, right? Where for every, basically what you have is we get a verified program of Backpipe, which we extract to Racket, and then we can run that program with any specifications and configurations that you want. Okay. So in summary, what I've talked to you about is SpaceSearch has two components so far, right? It has an interface and semantics that we can program against, but it also has this extraction mechanism. There are many more things in the paper that I won't talk about here. For example, we can also handle infinite search spaces, which are then extracted to certain SMT logics. There are other backends that we support other than Rosette. We have things to do parallelization, so we can split the computation over multiple clusters, and we have incrementalization. Okay, now to the evaluation. We evaluated SpaceSearch by building kind of free tools out of this, free solver-aided tools. The first one I already talked about. That's Backpipe to verify BGP configurations. The next tool that we built verifies the equivalence of SQL queries. And the last tool that I built verifies the equivalence of different x86 semantics. So let's start with the first one. We take a specification and a configuration and get counterexamples, right? And this is actually a real tool. This isn't just like a little prototype. This takes real BGP configurations from real-world ISPs with hundreds of thousands of lines of code. And we can then verify real specifications that we've taken from the literature and Jupyter manuals and how to configure your routers correctly and so on. And we were able to then verify 14 of these specs, and we were finding actual errors in these BGP configurations, and our tool didn't find any faults, or didn't have any false positives. Okay. Now, the second tool that we built verifies the equivalence of SQL queries. So how this works is that the tool takes two queries, and we want to prove them equal. And this is useful, for example, if you have a compiler and one of these queries is an optimized version of the other one, and you want to know that they're equivalent. Now, showing the equivalence of SQL queries is actually hard because it means for all possible tables, they return the same result. So this is, again, quantifying over infinite spaces, which is generally hard. So we used a cool trick from the database literature that tells us that for certain queries, namely conjunctive queries, we can, it suffices to only look at a finite space of these tables. And so we implemented an algorithm that actually does this. And then we verified it correct in Coq, and we were able to extract it using our library to SMT, so it actually runs very efficiently. Last but not least, we verified the equivalence of two very different x86 semantics. So one of the semantics that we had here was the Stokes semantics, developed in Stanford for, it's a semantics for x86 that's targeted directly to SMT. And then we also use the semantics developed by Greg Morissette that is written in Coq. So we have a Coq x86 semantics. And what we're going to do with this framework is that for a given set of instructions, we're going to actually prove that these semantics are equal for all possible machine states. So how we do that is that for each instruction, we bind over the whole space of possible inputs. This is a little simplified here. And then we do the same trick where we return empty and singleton if they're equal or not. And using this procedure, we found 7 bugs in rock salt. And we also found 1 bug in Stoke. And the maintainers of these tools are really awesome, and they fix them and work with us to really help us and make sure that this stuff gets fixed. So let me talk about some of the related work. There's been a lot of development recently in the domain of solver-aided languages. And if you're familiar with that term, you can think of SpaceSearch as just a solver-aided language for Coq. Now, there have been others. For example, Rosette is a solver-aided language for Racket, and Smitten is a solver-aided language for Haskell. Now, there also have been verified solver-aided tools before. So Xert is one of Zach Tedlock's projects, which he actually verified that his solver curls are correct, but he didn't provide any general methodology for people to use. Lastly, I want to make sure that it's clear that SpaceSearch is not a verified SMT solver. It's also not a tactic that invokes an SMT solver. Instead, it's a library that allows you to build these solver-aided tools and then extract them to run them efficiently. That's all I have. Thank you very much. And the tool is open source.